Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge, minimum time to collect all apples in a tree. So basically what we have is we have this tree here, and there are some designated nodes where there is an apple, like 2, 4, 5 here. And what we want is we want to start from 0 and collect all apples, and then return the minimum time we need to collect all of them, okay? Now, one thing you notice here is that if we go to 4, we'll go down here and then go down to 4 and then back up, right? And each edge we traverse is going to be count as 1 second in our time here. And so to get to from 1 to 4, we have to go to 4 and then back up to 1 so that we can go to 5. So here we get cost of 2. And same thing for 5. To get this 5 here, we go down and go up, and this incur cost of 2. And similar, to go from 0 to 1, and we have to go down and then go up. And here we incur a cost of 2 because we need to go there to get these apples. So that's important part. Now let's take a look at this example. So you can see it's we get it in a format of a graph and not a format of a tree. Basically, this means there is an edge between 0 and 1. This means there is an edge between 0 and 2, and you get the idea. And in has apple list, the positions that have true means there is an apple in that node, right? So for example, here there is a position 2, it's true, so that means there is an apple at position 2, okay? So for example, for this one, if we count it, we go down here, so 2 from this, 2 from this, and 2 to bring both apples up, so 2 here. So overall 4, 6 for these two, and then here 2 for this one, and so overall it's 8. That's what we have here. So that's the idea. Now how do we solve it? Let's see how do we solve it. Okay, so let's see how we can solve it. This is the example we have in the first example we have is this one. So how do we do it? Basically what you can see here, one observation that we can make is that if you have a node where there is an apple, like 4 here, we will need to go twice. What does that node need to tell its parent in terms of the time it takes to collect that apple? Well, it needs to tell it 2. Sorry, because we need to go down to 4 and then we need to go up. So we need to tell it 2. That's the most important observation. But once there is an apple, right? Once there is an apple in one of the children, we have to propagate that apple up to the root. And so even though 1 doesn't have an apple, we still need to go down to 1 to get to 4, and we need to go up to get to 0. So we incur a cost of 2 here. And here, because both have the same parent, we incur it only once because we go down only once. So that's also important, right? And so in terms of how to solve this, we can think, okay, maybe let's just use DFS, right? Let's just use DFS. And what's important with DFS is what information does the child need to tell the parent. And the information is, if there is an apple, it needs to tell it that we need 2 time of 2, right? And what does 1 need to do as a root? It just needs to collect the time for all of its children and add it up together, right? And so for a node, we definitely know that for a node, when we are traversing a node and going through, since we get the edges in a graph format, we'll do it in a graph format, so it would be in graph of node. And we'll, of course, change this edges array to be a map from keys to a list, from a node to a list of its neighbors, right? So that it's easier to do this, right? And so, because this is a list of A and B, and that would be hard. We would have to traverse all the list and check if the first node is equal to A. So it's also bidirectional, so we would have to check if this is the node or this is the node. So it's a little bit hard. So we just use a map, and that would be easier, right? So that's a pre-processing step we'll do. But what does a node needs to? So for example, this one here needs to say to the parent that it has 4 and then it adds 2 for itself, right? And so here it just needs to collect the sum of whatever its neighbors tell it. So we would need to have some result or some time count here. Let's call it time, right? And we need to just collect the time for the sum of the time for all the neighbors, right? That's what we did here. 2 from 4, 2 from 5, and we added up together. If, let's say, 5 was not a child, doesn't have an apple, then it will just report 0 and we'll add 2 as 0, right? So that's one thing. Now, what about the node itself, which is what we need to process here? Well, the node itself needs to check if it has an apple, right? Then it needs to say 2. That's what for here. It needs to tell 2 to its parent. So whatever time, so let's say 5 has other children here, right? And they didn't have any apples. So time would be 0. Then it will still need to add its 2 because it has an apple, right? And so if the node has an apple, we will need to say time plus 2. Okay? Now there is just one case, which is what if the node at position 0 itself has an apple? Well, there we don't need to count anything because we start there. Okay? Because we start there, we don't need some time to go there. So except for node equal to 0, we don't need to incur any time. And so for that, we need to do a special case here. So, and we need to do node is different than 0, because if it's equal to 0, we don't need any time. Now, so if there is an apple, we need to add 2, but also there is this case here that I said here, where if any child has an apple, we need to incur the time to go to the parent so that we can go to the child. And so we need to add 2 if the time is bigger than 0. So if any of the children has an apple, let's say if it was just 4 and 5 didn't have an apple, we still need to add this 2 to go to 4. Or let's say if it's 5. Or even if there were like a subtree here and only way down there is a node that has an apple, we need to incur the cost of going to 1, right? And so for that, if any of the children has an apple, then we want to add 2. So how do we do that? We can just check if the time is bigger than 0, that means there is a sub child that has, so, or here, if time bigger than 0 or the node has an apple, then we need to add time of plus 2. So that's the idea. And of course, we'll do the normal DFS traversal of having a visited set so that we don't visit a node multiple times. But this is the core idea here, is that we will traverse, collect, and then add 2 if either it has an apple or one of the children has an apple, right? And then we'll exclude node equal to 0. Yeah, so that's pretty much the idea. Now let's code it and make sure it passes. Okay, so let's code up this implementation. So the first part is, of course, we'll need to create our graph. I'll just copy paste it. So we need an undirected graph, which means for every edge here that has A to B, it's undirected. The problem tells us it undirected. And so we need to add both A, B, and BA, right? So that's the first part. Now we need a visited set for our DFS. And we need to start our DFS from 0, and then we can do what we said in the overview. So for our DFS, of course, we need to, when we visit a node, we need to add it to the visited set. And if the node is already visited, we don't want to visit it again, so we can just return 0 because there is no, we already calculated whatever time we need from it. And now we will do, we'll traverse the children, so we'll go through in graph of node, right? And then we'll just do DFS on the neighbor, and then we will add if there is an additional time. Then we'll add it as we said in the overview, and then if, now we will do the check if any child has an apple or if this node itself has an apple, okay? But with the condition, we want to exclude node equal to 0 because there we don't need any time to go to that node. Then in that case, we want to add 2, the time to get to that node. And then we can at the end return time overall to the parent. And that should be it pretty much. So let's run this. Looks good, let's submit. That passes test cases. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.